Introduction. My name is Johan Stefanovic. I'm a principal researcher at Microsoft, and I'm going to tell you about an exascale archival storage system that we've designed and prototyped over the past 7 years inside Microsoft Research that's currently being productized. Now, before I start, I just want to set the scene a little bit because this is not your usual SOSP talk or project. Silica is the largest project we've ever undertaken inside Microsoft Research. In designing and prototyping the system, we've had to innovate across all of these areas you're seeing here, from basic research in physics, materials processing, microscopy, to machine learning, industrial design, and much more. And this is really because we've built Silica from the ground up and cross-optimized everything from the materials level of the media all the way up to the cloud service. And each of these boxes could be several talks on their own. For this talk, I'll focus more on these parts, but I'll briefly have to touch on everything just to kind of give you a sense for how it all fits together. I will have to skim over lots of things, so please read the paper for more details on everything. So the main motivation for this work is really that despite the burning need we have, we still do not have a storage technology that offers sustainable and cost-effective long-term archival storage. The most cost-effective media today are magnetic media, like hard disk drives and tape, with tape offering the lowest dollar per terabyte cost. And these technologies underpin archival storage in the cloud today. Of course, the problem with these is that magnetic media has limited lifetime, and it degrades over time, which means that every few years we need to refresh the data by copying the data onto a new generation of media. With hard disk drives, this is on the order of 5 years. With tape, it's on the order of 10 years. Now, in the interim, we also need to expend energy continuously in the systems to scrub the media. So this means periodically reading the data back, recomputing any sort of checksums, using erasure coding to fix up any residual errors just to guarantee the data's durability. And of course, the consequence of all of this is that the emissions, the energy, and the cost to store the data scale with the lifetime of the data with these technologies rather than just the operations that you perform on it. And so we believe glass offers a truly disruptive media for archival storage. Glass is a low-cost material. It's a very durable media. It's a chemically inert material with virtually unlimited lifetime in the face of many environmental conditions, like heat up to the melting point of the glass, water, even surface-level scratches. It's impervious to electromagnetic fields, things like magnets, EMPs, solar flares. It's a warm media, which is actually impossible to overwrite even by accident or maliciously, and I'll talk a bit about that a bit later. And it doesn't suffer from any sort of bit or media rot. It gives us data lifetimes on the order of thousands of years, and it means that we don't need to scrub the data. Of course, all of this means that we can leave the data in situ forever once it's written, and our goal in building a storage system around this storage medium is to achieve what we call operational proportionality, which is that we want the emissions, energy, and cost to store archival data to scale with the operations performed on it rather than with its lifetime. So I'm going to tell you how to build such a system. So to write data, we use ultra-fast femtosecond laser to write multi-bit voxels inside the glass media. This is a physical process that was originally discovered at University of Southampton. At the top there you see SEM image of 4 multi-bit voxels, and what we actually do in practice is we write 2D sectors with over 100 kilobytes of data each, and on the left here you see a photo of what one of these sectors looks like from our prototype hardware. Now, we write data in glass platters that are square, and they're roughly the size of a DVD across. And we've made a deliberate choice to not spin the media. Spinning media is very difficult to spin and stabilize at high RPMs, particularly when you're doing short random reads, and I'm going to talk about why that's important later. So instead, we've chosen to move the light. So to achieve high throughput in the system, we use what's called a polygon scanner, which is similar to the kind that you have in the barcode readers that you might have at the supermarket. And what we actually do is we scan the laser beam across the surface of the glass, as you can see, and we focus on different points inside the glass. So we scan in 2 dimensions, and then we stack multiple 2D sectors in Z, filling the glass volumetrically with hundreds of layers of data. Writing is the most expensive part of our system, and in the paper we discuss how to maximize write drive utilization at the system level in order to minimize costs. Now, reading is done with a totally different technology called polarization microscopy. It's much lower cost. It uses very low powered illumination. You can even use LED lighting for this. And it's fundamentally impossible to overwrite the data while reading it, even by accident. You really need a femtosecond laser to create the physical changes in the structure of the material. So to read, what we do is we focus on the sector of interest at the depth of inside the glass that we care about, and we image an entire 2D sector at a time. And then to read what we call a track, we basically scan in Z depth first, and effectively here you saw what is essentially a sequential read. Now, a key advantage of Silica as a media is that fundamentally it's a random access media. We don't require any sort of spooling. We simply mount a glass platter into a reader, and once it's mounted, we can quickly seek to the location that we care about, and then just read as little data as we want before we eject and we move on to the next platter. To decode the data, we use machine learning, not because it's hot and popular at the moment, but because it actually gives us the most accurate analog to digital signal conversion. And this is compared to kind of traditional signal processing techniques. So what we do is we take the images acquired by the readers of the 2D sectors, and then we stream them to our ML decode stack, which runs as a fault-tolerant elastic microservice. And to decode them, we use a fully convolutional neural network that we designed in-house. Those of you familiar with medical imaging might recognize this as a variant of a UNet. And what we get out is we feed images of the sectors in, and then we get out probability distributions for all of the symbols in the sector, which we then feed subsequently into error correction. Now, taking a data-centric view of the system, if we look at the life cycle of data in a Silica system, data is first staged for several days to smooth out peaks in the incoming write rate. We then perform all of the relevant error correction and erasure coding. And then we write many platters at a time, all of which are part of the same erasure coding set, which allows us to recover data even in the presence of unavailable platters. Now, verification guarantees the durability of data stored in Silica. Since the read and write drives use fundamentally different technologies, we read every written platter just once in full with the read technology that will be used to read it subsequently. Since the media or the data do not degrade, we only need to do this once, in contrast to magnetic media that requires constant scrubbing in between media migrations. And finally, data spends the rest of its life at rest without consuming any sort of energy, only being loaded into a read drive when on-demand reads are issued for it. Now, when designing a cloud-scale storage system around the core Silica technology, we wanted to go beyond using just our intuitions and heuristics, and so we decided to study real systems to understand what do archival workloads really look like in practice, in production. So to do this, we studied a set of geo-distributed tape libraries that underpin a multi-tenant cloud archival service with SLOs upwards of 10 hours. And we found some very surprising things, many of which go against the conventional wisdoms in the community about what archival workloads really look like. The first is that archival workloads really require a lot of flexibility. So if you look at the long-term average across operations, there are 47 times more megabytes written than read, and 174 times more write IOs than read IOs. So the workload is mostly write-dominated, with a small amount of data being read back, which means that the write and the read bandwidths really need to be able to be provisioned and scaled independently in the system. Tying them together in drives that can both read and write just doesn't make any sense and would be extremely wasteful. The second part is read variability. So in this graph, you're seeing the ratio between the tail and the median throughput across different data centers. And you can see a large amount of variability, up to 7 orders of magnitude peak to mean ratio within data center. And across different data centers, you can see over 5 orders of magnitude difference. And the consequence of this is that our library design really needs to be modular and flexible to allow different amounts of resources to be deployed to support this variability across different deployments. Now, when people think about archival storage, most people think about sporadic, very large, many terabyte reads, like a disaster recovery workload. But actually, it turns out archival workloads are IOPS dominated. So on this graph, we see on the left-hand y-axis the percentage of all read IOs, and on the right-hand y-axis we see the fraction of total bytes read across the spectrum of file sizes on the x-axis. And we see a very skewed distribution. 58% of reads are for files smaller than 4 megabytes, but they only make up 1.2% of the bytes read in the system. Conversely, 85% of bytes read are for files larger than 256 megabytes, but they only make up 2% of the total read requests. And we see 10 orders of magnitude range in the file sizes. Now, this means that individual per drive read throughput is less important in a workload that is mostly dominated by smaller read IOs. And for the small fraction of large files, having a sensible sharding policy that takes into account drive throughput, number of drives, and the SLO you're trying to achieve in the system becomes quite important. But the most important takeaway when building an archival system around to service this workload is that we really need to minimize mechanical overheads in the system. Things like media transfer, mounting, and seeking delays. And servicing such a small read IOPS-dominated workload with a tape library is actually very hard. Requests in a tape library spend most of their time queued, the media is disaggregated from the drives, and media movement becomes very important to the latency and the goodput of the system. In a tape library, there's only a single robot operating on a gantry, so the media movement is fundamentally sequentialized. And magnetic tapes are fundamentally a spooling medium, which means that even once mounted, we'd sometimes need to wait as long as a minute before we can start performing an I/O. So we took these observations to heart and as kind of core design principles when building the Silica library, and which is that we need to be able to provision and scale the write and the read bandwidths independently in the system, and we really need to minimize the amount of mechanical overheads in the system to be able to service such archival workloads. And we added two other principles which we really believe are important to allowing us to achieve operational proportionality. The first one is that data at rest should never consume any sort of resources. And the second one is that the library lifetime really needs to match the lifetime of the data center building it's deployed in without requiring any sort of mass migration of media and so on. So I'm going to show you a kind of a sketch of a minimal Silica library so you have some idea of how a library comes together. We have a write rack, which writes multiple platters concurrently on the order of 8 to 10 platters. We have a read rack, which can hold 20 glass platters at a time and read around 10 platters concurrently. And then we have several storage racks, which are passive, so they don't consume any sort of power. They simply provide storage for platters. And at the end, we have another read rack for fault tolerance in case we get a partition in the middle of the aisle. Write, read, and storage racks can be independently scaled as needed based on the workload characteristics in the library. And I'm going to show you now a prototype that we've built in our labs of what one of these libraries looks like. So this design was inspired by warehouse robotics, and it's quite different to the expensive single gantry robot in a tape library. You can see we have passive storage racks here that don't consume any sort of power. We have raw glass platters that are stored in the shelves, in these little shelves, a bit like a bookshelf across the height of the rack. And the platters are handled by these little robots that we call shuttles that can move horizontally down the rails, but they can also do this crabbing motion when they move between the rails, which is very important because it gives us all-to-all addressability between media and robots. So it's great for fault tolerance, and it's also great for flexibility in terms of how we get the media to the readers. Of course, shuttles can also pick and place platters, so they can move them between different slots in the library and between slots and readers. So shuttles fundamentally parallelize media fetching in contrast to a tape library. Whereas everything is sequentialized in a tape library, shuttles can parallelize the fetching of the media. And more importantly also, or equally as importantly, shuttles can be added and removed and redeployed dynamically from a library as the temperature of the archival workload changes. So we can redeploy shuttles between different libraries based on the age of the workload and customer requests. So to evaluate the performance of an archival, a whole cloud system backed by Silica libraries, we use a discrete event simulator seeded with data measured from our library prototype and cross-validated where applicable. In this case, you're seeing a cross-validation graph of shuttle movement. And to do the actual evaluation, we use traces, real workload traces from the system I was just describing before in the analysis. What we did is we looked at across 6 months at every rolling 12-hour interval, and we picked 3 representative traces. Typical, which is a typical 12-hour period. IOPS, which is the 12-hour period with the most number of read IOs. And volume, which is the 12-hour period with the most number of bytes read. And in this talk, I'm going to focus on 2 evaluation questions, but there's tons more in the paper. The first one is, what is the impact of read drive throughput on system SLO? And the second is, can we achieve high read drive utilization with our design? So to answer the first question, we simulate a data center-sized service backed by Silica libraries. Each library has 20 drives, 20 shuttles, so 1 shuttle per drive, and we made the number of platters in the system be proportional to the total amount of data stored in the archival system at trace time. And our metric is 99.9th percentile tail latency, and our target is to achieve an archival service SLO of 15 hours time to last byte, which is in line with many archival service offerings out there today. Now, you might expect, especially for the bandwidth-intensive workload, that you might need tape-like throughputs on the order of hundreds of megabytes. You know, some tape drives do as high as 400 megabytes a second. But actually, all of the workloads that we evaluated finished within SLO, even at 30 megabytes per second. And we see actually diminishing returns past 60 megabytes per second, even for the volume workload. And the crucial thing to achieving all of this really is minimizing mechanical overhead. And Silica has a distinct advantage here coming from several things. One is we use a media that is random access in contrast to spooling tapes. 2 is the library design with the many shuttles parallelizes media fetches in the system. And our design choice to make the media non-spinning means that we don't need to wait for the media to spin up and stabilize before we can perform a small read. And the paper further breaks down the contributions of shuttle mechanics and management to per IO latency, which are subsumed in this graph. So if you'll recall, I mentioned that the read workload is bursty. So read drives need to be provisioned for peaks, which means that during non-peak periods, there is spare read capacity in the system. So we've designed the read drives to have 2 slots and a fast switching mechanism that can quickly switch the optical path from reading one platter to the other. So by doing this, we can essentially pipeline 2 different read streams. You can think of this as a physical realization of double buffering. Recall also that I said in Silica we need to verify, or we choose to verify each platter once just after writing. Verifications are less time sensitive since they can be delayed simply by keeping the data stored in or buffered in a higher level tier for slightly longer. And in this experiment, we evaluate the effectiveness of this fast switching mechanism to maximize drive utilization by pipelining verifications with on-demand customer reads. So the experimental setup is the same as in the last slide, and we actually see that we're able to get over 96% drive utilization across all of the 3 workloads. And in the figure, you're seeing the breakdown of time spent on customer reads versus verification. Obviously, for volume and IOPS, we spend more time servicing customer reads, the most being for IOPS, since to do many random small IOs, we need to load and mount and then unmount and unload many more platters. So fast switching is actually a great efficient mechanism to achieve high drive utilization. There is a ton more stuff in the paper that I didn't get a chance to talk about. More workload analysis. There's 2 whole sections on durability and availability, talking about the kind of error correction and erasure coding that we use, which is actually quite different than what you might expect, so please go read that. More evaluation, some discussion about incumbent technologies. And I just want to end by thanking my amazing team of colleagues and collaborators. It's a truly multidisciplinary team with really amazing people without whom none of this would have been possible. Silica is an ongoing effort with over 150 person years put into it so far. If you're interested to see actually what data looks like in glass, we have a microscope set up at the booth just in the coffee break after this session. And yeah, last thing, I want to thank you for listening.
Thank you. All right, I don't know who was first. Okay, let's start in the middle.
I was technically lost, but I guess I'll go. Okay. Thank you for the amazing talk. I have a couple of questions. The first one is around error correction as well as the number of read requests that technically fail, because you have an analog to digital processor after the read, right? So could you comment on like how many read requests are actually failing in that after your erasure coding as well? Yeah, so
just because we use machine learning, it doesn't mean the media is probabilistic suddenly. So we use, any storage media has analog to digital signal conversion. It's just that for most media, it's packaged and it's wrapped under the covers. We use LDPC per sector, just like flash and hard disk drives use. The only thing we use is, instead of doing kind of traditional signal processing to get probability distributions for, what is this symbol, we use a neural network, and then those distributions go into the LDPC. We do error correction, just like other media, and then on top of that, we do erasure coding, and we make some different choices. But fundamentally, there's nothing fundamentally probabilistic or different just because of this. We simply use a different analog to media conversion, but we can leverage the same kind of error correction and erasure coding that systems do use today.
So there's no difference in the failure rate that you would see with the systems? Okay,
no.
Thank you. Can I
and just like any other storage media, you just need to provision enough error correction based on the expected raw error rate. Yeah.
Thank you. Okay, another question on my left.
Hello, this is Jia Huan from Shanghai Jiao University. Very interesting work, and my question is that I'm curious about the storage density compared to traditional media like HDD or SSD. Thank you.
Yeah, so I didn't mention that here. We have talked about that in a different talk that's up online. If you work out the volumetrically, if you compare, we're roughly on par with LTO9 tape.
Okay.
If you, considering that LTO9 tape is a spooled media and we're a volumetric media.
Okay. Nice. All right. On my right.
Okay, thank you. Thank you for your nice and great talk. I'm Wei Junyu from Tsinghua University. And if I missed something, I'm sorry, but I want to explain what is the most significant advantages of the glass-based long-term storage compared with the CD-based long-term storage.
CD-based?
Yeah, CD-based.
Yeah, there are several, but fundamentally CDs are still a manufactured media. They're still made from thin film material, sandwiched, glued between polycarbonate material. The media does degrade. If you talk to people who have built archives using CDs, the media actually degrades in a few years, and so you don't get away from the problem of having to refresh the data and move it to a new generation of media every few years. Also, CDs fundamentally are limited in the number of layers they can write, so you can't achieve quite the same densities as we can with Silica, because in order to write layers further down, you need to focus the laser beam through many layers of material.
Okay, thank you. It's quite helpful.
Thank you.
Okay, second to last question on the left, and then after that, the last question in the middle.
Hey, Phil Levis, Stanford and Google. So first of all, this is awesome. I've been waiting to hear about this ever since I first started hearing about it, and it's just great to see all the wonderful work you've done. So I want to go back to the density question. I'm wondering, what are the limits here? Like, you have a particular density now, given at some point you'd have to go to higher frequencies than your UV and you kind of end. How much further do you think you could take this?
So that's an interesting question. We are exploring this. I think there's certain kind of obvious physical limitation, like diffraction limits that come in at one point. We are exploring ways of going beyond that. I think we've already talked about this publicly. We do actually kind of have a technique to go beyond the diffraction limit already for this generation, but it's also a question of material. So we're exploring multiple ways, but I can't comment on a concrete roadmap right now. Like how frequently is the density going to double right now?
Awesome, thanks.
Thank you. All right, last question.
Peter Chen, University of Michigan. Very impressive work. I'm wondering if you could speculate on how you think the performance characteristics of Project Silica might affect the workloads that it supports.
Yeah, great question.
Or do you think those are static and not going to change?
Well, so our goal, I guess, in the evaluation so far was to make sure that we can actually efficiently service the workloads that we see today. I guess you're asking the reverse question of what kind of
new workloads might this enable?
Yeah, so I think first there is a very large market of people who want a highly resilient media that is much more resilient than existing magnetic technology. So I think there's likely going to be many more customers who are suddenly using archival storage in the cloud because we're able to offer a different media. So that might increase the volume in terms of workload. In terms of performance characteristics, it's a cost-benefit trade-off. So I mean, if you want to invest more to offer perhaps better SLOs, that might change the number of people who want, for example, something closer to an active archive service. But I think primarily it would have to do with just the scope of the number of business sectors who would suddenly be interested in that. You would have a lot more archival data now coming into your system. In terms of what the actual read characteristics graph would look like, what would the distributions look like, I'm not sure really. I think it's really up to the customers. We were very surprised actually to see that the workload was actually so IOPS dominated. So it's a bit of an unknown, but yeah, interesting food for thought. Thanks.
Thank you.
All right, thank you.